Okay, hello and welcome everybody to this week's special random geometry colloquium. Today, we are really glad to have Arghya from Chennai Mathematical Institute who would give a talk on a higher dimensional analog of Margulis' construction of expanders. Over to you, Arghya.
Thank you. Thank you very much for inviting me to give a talk. So the talk will be in three parts. I will start by description of the results. Then I will give outline of the proof. And then I will talk about some examples. So let us start with the description of results. I have been advertising my result as a higher analog of Margulis construction of expander graphs. So first I should recall what is Margulis construction of expander graphs. So this goes by considering quotients, finite quotients of Cayley graph of a group with property T, and that gives expander graphs. So I have to tell you what are expander graphs, and then I will tell you what are Cayley graphs and what is property T. So expander graphs are a family of sparse but highly connected graphs. So what do I mean by sparse and what do I mean by highly connected? So sparsity is not the property of one particular graph, it is the property of the family of the graph. So suppose I have a family of finite graphs, and I assume that the vertices, the set of vertices which I denote by xi0, this goes to infinity. But the sparsity means that even though the number of vertices go to infinity, the number of edges coming out of a particular vertex remains bounded. So degree of V, I take supremum over all I and all V belonging to xi0, that is bounded. And what do I mean by high connectivity? It means that I should not be able to cut my graph into two pieces of more or less the same volume by just cutting a few edges. So suppose I have taken a partition of my vertex set into two parts. Let's say part A and part B. There is a set of vertices, and then I look at the number of edges connecting them. Let's call the set of edges connecting them AB, and I look at the ratio AB by number of vertices in B, number of vertices in A, and number of vertices in B, and I take minimum of that. So this ratio basically tells you how difficult it is to cut the graph into two parts. How many into two more or less equal parts. So, and I look at infimum over all such partitions of the vertex set, disjoint partitions, and this is called the Chigger constant. And so what I want from my expander graphs is that h of xi is bounded with. So these two conditions, bounded degree and uniform lower bound for the Chigger constants, these two together tells me what is these two properties mean that my family of graphs is expander graphs. Okay. Now let me tell you what is a Cayley graph. I think, okay, this does not really need an introduction, but just take any finitely generated group and you take any symmetric finite generating set, and then the Cayley graph is a graph which is labeled by, whose vertices are labeled by elements of the group, and two vertices which are labeled gamma 1 and gamma 2 are joined by an edge if gamma 2 inverse gamma 1 belongs to the generating set. But there is an alternate description of this, which will be useful for me because I want to look at higher dimensional generation of this stuff. So suppose Y is a K gamma 1 complex. By that I mean that the fundamental group, this is a CW complex, and the fundamental group of Y fix some base point. This is exactly gamma, and all other homotopy groups are 0, including the 0th homotopy group, which means that it is connected. So in other words, the universal cover of Y is a contractible space, and gamma acts, there's a covering space action, so acts by covering transformations. And then if you look at the one skeleton, okay, I want to put one more condition. Assume that Y has exactly one vertex. That is, its 0 skeleton consists of only one point. Then the one skeleton of the universal cover is a Cayley graph. Right. Okay. Now let me tell you what is property T. So a group gamma is said to have property T if the first homology of the group with coefficients in any unitary representation vanishes. And so this in fact has a nice geometric interpretation, which is that if I look at any isometric action, affine isometric action of gamma on any Hilbert space, then it must have a fixed point. So this is same as the vanishing of the first homology. Sorry. And then let me tell you what is the construction. This construction is originally by Margulis, but he did it for a special case, and in general it was done by Alon-Milman. So you take any discrete group having property T, and if a discrete group has property T, then it is finitely generated. So you take a finite generating set S, and you consider its Cayley graph, and you consider a family of finite index subgroups, which are becoming...
You probably need residual finiteness for this.
Yes. Yeah. So you want residual finiteness so that you can look at a family of finite index subgroups which becomes smaller and smaller. And then, that means that if I look at the quotient of the Cayley graph by these subgroups, these will be a bunch of graphs which are becoming larger and larger. And the claim, and what they showed is that this family of graphs, these are expanded graphs. Right. So now that I have told you what is the Margulis construction, let us try to see how this can be generalized to higher dimensions. So I have to tell you three things. What is the higher dimensional analog of expander graphs, Cayley graphs, and what higher dimensional analog of property. So let me start with the higher dimensional analog of expander graphs. So I said that this Chigger constant captures the meaning of the graph being highly connected. It's a geometric quantity associated to the graph, but there is also an analytic quantity associated to the graph, which also captures the meaning of being highly connected. And the other good thing about the analytic quantity is that it has a ready generalization to higher dimensions. So that analytic quantity is basically the Laplacian, the graph the first non-zero eigenvalue of the graph Laplacian. But let me do things in full generative. So let us look at a finite simplicial complex X, and let us look at its simplicial chain complex. So what that means is that, suppose you look at Xi this is the set of high dimensional simplices, and Ci of X is all functions from xi to, let's say, c. Let's work with complex numbers. In fact, yeah. Let me give you some examples. For example, if suppose sigma belong to sigma is a I simplex, then you can look at a data function, which means that this is a function from xi to c, which is 1 if sigma equal to tau and 0 otherwise. Right. So the reason I gave this example is because this delta sigma, these guys, they are a God-given basis of the quotient groups, quotient vector spaces. And if God gives you a basis, then you should declare this basis as orthonormal, and that gives me so this gives an inner product on CIX or RX. And then what you can do is that because you have inner products on all the quotient groups, you can look at the adjoint of the co-boundary. Adjoint of T, and then you can define Laplacian. So the Laplacian is like d star plus d star d. This is the usual Laplacian. This is just like what happens in the Riemannian geometry. And then only d star d, which is basically you go on to the right and come back. That part is called upper Laplacian. This is the one that I will be using in this talk. And you have this lower Laplacian, which is the remaining part. And then you have what you have is the set of co-boundaries, which is the image of the co-boundary map. And you have the kernel of the co-boundary map, which is the set of co-cycles. By the way, this set of co-cycles is also the kernel of the upper Laplacian. And then you define something called the spectral gap, which is the first non-zero which is the least eigenvalue of the upper Laplacian when it is restricted to the perpendicular of the co-boundaries. In fact, note that if my cohomology, if the cohomology is in the ith cohomology is non-zero, then this guy is exactly equal to 0. Spectral gap is 0. And then there is something called essential gap. So, which is the least eigenvalue of the upper Laplacian when it is restricted to perpendicular of the set of co-cycles. And note that this guy is the first non-zero eigenvalue of the upper Laplacian. And also there is something else I want to say. If HIX is equal to 0, then the spectral gap is same as the essential gap. So this will be okay. So I said that there is this analytic quantity which is a stand-in for the Chigger constant. So how do I say that? So there is this Chigger-Buser inequality, which was proved by Chigger and Buser for manifolds and by Dot-Zwick and Alon-Milman for graphs, which is that this lambda 1 of x. I just would like to point out that the way I frame this, I would also like to consider not just the simplicial chain complex, but the augmented simplicial chain complex, so that this makes sense. Anyway, so in case of graphs, you just have this is the all chain complex and effect C minus 1. And so you look at D and D star, and then that is the Laplacian, and you look at the first non-zero eigenvalue of the Laplacian, maybe just call it lambda, and that is bounded by the Cheeger constant, twice the Cheeger constant on one hand, and the square of the Cheeger constant divided by 2n, where m is the maximal degree of the graph. So note that as if hx goes to 0, then lambda x has to go to 0 and vice versa. And also, I mean, what hx measures is how easy it is to disconnect the graph. And if the graph is disconnected, then lambda x is equal to 0. So lambda x is kind of an analytic way of saying how easy it is to disconnect the graph. Okay, so now I can give a alternate definition of expanded graphs, which is basically I just replace the Cheeger constant by this analytic quantity. So I look at a family of finite graphs which are of bounded degree, and I would like the first non-zero eigenvalue of the Laplacian. These are all connected graphs. This guy to be bounded below. Okay. So now this definition lends to a ready generalization. So let me talk about higher spectral expanders. This is a definition given by Lubotsky in his 2018 ICM talk. So you consider a family of d-dimensional finite simplicial complexes, and you want them to be of bounded degree. That is the number of simplices containing a vertex, a fixed vertex, is bounded above. And also you want this lambda j of xi, this guy, to be bounded below for all j between 0 and d minus 1, and for all I. So this is the definition of higher spectral expanders. And then I have to tell you what is the higher dimension analog of Cayley graphs. So this is again presents itself from the way I formulated the definition of Cayley graphs, the alternate definition of Cayley graphs. So this is just consider the n-Kazhdan of the universal power of a k gamma 1 complex. And I just call this is a mouthful, so I'll just call it a Cayley n complex. By the way, in literature, when people say Cayley complex, I think they mean the Cayley 2 complex. Okay, so there are a few problems with this in the sense that what I want is I would like to look at finite powers of the k gamma 1 complex, which will give me finite simplicial complexes. So the first problem is that the n skeleton of the k gamma 1 complex need not be finite. And the other problem is that it need not be so this is a priori only a CW complex, so it need not be a simplicial complex. Actually, this is not really a problem, as we will see. So for the first one, I just forcefully make it a finite. So I only consider groups of type Fn, that is there exists a k gamma 1 complex with finite n skeleton. And for the other problem, that is not really a problem, because there's a classical result of Whitehead, which says that any CW complex is homotopy equivalent to a simplicial complex. And in fact, if you start with a finite CW complex, you will be able to find a finite simplicial complex which is homotopy equivalent to it. So that is the kind of k gamma 1 complex I will start with. So in summary, if I have a group of type Fn and I look at its Cayley n simplicial complex, and suppose again let's assume it's finiteness, and so I look at a family of finite index subgroups, and I look at X mod gamma I. So these are this is a so my claim is so from our discussion, this is a family of bounded degree finite simplicial complexes. Right. Okay. So I found analog of expander graphs. I found analog of Cayley graph, and now I will consider the analog of property T. By the way, property T, in the way I formulate it, this may also be called n-Kazhdan. This is a terminology of T and this. So sorry. So gamma is said to be n-Kazhdan if Hn of gamma pi, this guy is equal to 0. That was the nth group homology of gamma with coefficients in any unitary representation for all pi unitary representation. And this is gamma is said to be strongly n-Kazhdan if the cohomology with any unitary representation vanishes for all dimensions between 1 and n. So now I can state the main result, which says that let us look at a group of type Fn and look at its Cayley and simplicial complex, and I look at a finite index, a family of finite index subgroups. Then we can say that if gamma is strongly in Kazhdan, then right, do I want? Oh, yeah. Then X mod lambda I, these are n-dimensional spectral expanders. Okay. So if I want to continue, I have to talk about reduced group homology. This will be used in the group, but also, I mean, this condition of being strongly n-Kazhdan is superfluous. Just like the condition of having property T is superfluous for construction of expander graphs, because it is true even if gamma only has property tau with respect to the considered subgroups. So to talk about that, let me talk about reduced group homology. So how do you compute the group homology of a group with coefficient in some model? So you generally take a projective resolution of the trivial module, which is C, and then you look at
Arghya?
Yeah.
So do you want a reduced group cohomology to be 0 or the group cohomology to be? I mean, do you take the closure of the boundaries or do you not take closure of the boundaries?
I do not take the closure of the
say that again?
I do not take the closure of the boundary.
Okay.
Yeah. So generally, what we would do is we take a projective resolution and apply the Hom functor. But for our purposes here, we will only look at free resolutions. So I look at the resolution of the trivial C gamma module C, and this what this notation means is that this is a free C gamma module with generating set, free generating set, gamma. Right, and so now if you are given a representation of gamma, you should apply C gamma dash comma V pi. So V pi is the Hilbert space on which the position is acting. So you do that and you get a quotient complex. And this quotient complex, this is a quotient complex for the group homology. Right. So the thing is, if you look at the elements of this quotient complex, they are homomorphisms from a free C gamma module to another C gamma module. So such a thing, such a homomorphism will be determined by its values on the generating set. So I can think of this homomorphism group as just maps from yi to v pi. So this is just v pi to the power yi means like so many many copies of v pi. And what that helps me in doing is that v pi, I have, let's take a unitary representation. And so this gives me a product topology. So in general, if I have a quotient complex where each Ci are topological vector spaces and the co-boundary operator are continuous, then of course I can consider the usual group homology, but we can also consider the reduced group homology, where I take the ratio of the cocycles modulo the closure of the co-boundaries. So this is the reduced group homology. Also, I mean, we say that hi bar, if hi bar is equal to hi, we say that hi is Hausdorff. I mean, of course, because yeah, that point is closed. Right. Okay. So the resolution that I will always be working with in this talk, that is given by the chain complex of the universal cover of a K gamma 1 complex. So this in fact gives you a resolution of C, because I mean, what is the chain complex? This is basically a C combination of C linear combinations of the I simplices. And what are the I simplices? These are basically lifts of I simplices in Y. And if you fix lifts of I simplices, then all other, fix a particular lift of every I simplex. And if you look at all other lifts, they are related by a gamma translation. So you can write it, this as C gamma Y. So yeah, so this is the resolution that I'll be using all the time. Okay. So the if and only if result that I was talking about, which is the higher dimensional generation of the result that you will have a family of quotients of Cayley graphs to be expanders if and only if the group has property tau. That is that if you just again take the same setting, gamma is a group of type Fn, X is a Cayley complex, and you look at a bunch of finite index subgroups. And then the quotients are spectral expanders if and only if hi gamma, and then I look at direct sum, a Hilbert direct sum of L2 gamma mod lambda I. So I want these guys to be equal to 0 for all I between 1 and okay, let's say n minus 1, and for the nth one, I want it to be Hausdorff. That is, it is same as the reduced right? In fact, H1 of gamma direct sum L2 lambda, I mean, this, if you put n equal to 1 in that last condition, this is the equivalent condition of property down for gamma. Right. So this result follows from, okay, so this is, I call it the core result. So, so again, same setting, and you fix some k, which is, let's say equal to n, and you look at lambda prime k xi. This, I remind you, this is the essential gap for the upper Laplacian. And then this guy has a lower bound for all I, if and only if hk plus 1 gamma, right? Hk plus the k plus 1 cohomology of gamma with coefficients in the Hilbert direct sum of L2 gamma mod lambda I. This is positive. So once you have this, the if result follows, because the vanishing of the cohomology will with coefficients here will imply vanishing of all the cohomology of all the simplicial complexes, and Hausdorffness will guarantee, and then that will mean that essential gap is same as spectral gap, and Hausdorffness will guarantee that essential gap is, there is an essential gap, which means that there is a spectral gap if the cohomology vanishes. Right. So this is the result that I would like to give a proof of.
So
Yeah,
this Hausdorffness, it assumes the closure of the boundary, no?
it assumes that the boundary set of boundaries is closed. Yeah. Yes.
Yeah. So then why don't you look at the closed, I mean the reduced cohomology? And this is exactly the kind of problem that arises when you look at reduced versus unreduced.
Yeah. So I'm just saying that you want the cohomology to be reduced.
Yeah. Okay.
Right. So let me talk about the proof a bit. So the first step is to write the cohomology. In fact, the cochain complex of these simplicial complexes as group cohomology with twisted coefficients. So this is what I have written here. So suppose lambda is a finite index of gamma, and you look at, this is the simplicial cochain complex, and you look at the cochain complex of the group cohomology with coefficients in L2 gamma mod lambda, but this is actually coming from the resolution obtained via the chain complex of Whiteley. That is the one I'm looking at. And because of, and you will notice that in that case, this group is actually isomorphic to L2 lambda mod gamma to the power yi, and this is like a direct sum of Hilbert spaces. So I assume that yi is finite because of the gamma is of type Fn Hilbert spaces. So this has an inner product. So this isomorphism is in fact isomorphism of cochain complexes, and moreover, it's also an isometry. Right. So why should something like this be true? So if you look at the homology level, what is happening is that this X is a contractible space on which lambda acts. X is a contractible space, or at least n-Kazhdan of a contractible space on which gamma acts properly discontinuously and freely. But lambda also acts, so therefore lambda will also act properly discontinuously and freely. So X mod lambda is also a K lambda 1 complex. And therefore, this is the cohomology of that is same as the group cohomology of lambda with trivial coefficient. And that is by Shapiro-Lemma equal to the group cohomology of, this is gamma. Group cohomology of gamma with the co-induced representation, but co-induction from C is same as L2 of gamma mod lambda. Co-induced is same as induced and same as, because it's all finite index. Right. So how do I actually so at least at the cohomology level. At the cohomology level, we see that what I claim should be true. Right. And if you want to look at if you want a proof of this, so the way to do it is you express both the quotient complexes as functorial images of the chain complex of X. So if you want to so for the space, I go from the homology of X to homology of X mod gamma, which is basically C gamma Xi. Let's say this is I modulo lambda. So these are the I cells of X mod lambda, and this you can show that this is not equal to C, but this is C gamma Xi modulo some ideal into C gamma Xi. So this ideal is basically so if you look at C gamma to C of gamma mod lambda, the obvious map Ci gamma I goes to summation Ci gamma I bar, let's say. So this is kernel of this, which is a right module, right C gamma module is I. So you have this thing, and then you want to look at the homology, the quotient complex. So you just apply the Hom complex on C of this type. C. Right, and and here it's just as I said before, for the to get the quotient complex for the group cohomology, you just look at C gamma Y module comma sorry, this is L2. Right. So but this is isomorphic to because of all its finiteness conditions. This is same as this functor is same as the tensor product functor, and the tensor product functor you can show that this guy can be written as a composition of two functors, which is C gamma. Let us look at L2 of gamma mod lambda. This is the dual of the C gamma module given by C of gamma mod lambda, and then this is the right module. Yeah. So you first do this, and then you apply Hom. Right. And so all you need to do is you need to show that this first these two functors are naturally isomorphic. And that is true because I is the annihilator for the of an element in C gamma. So using that, you can show that they are these two functors. The first two functors are naturally isomorphic, and also then the isometry follows since you can keep track of all these maps since orthonormal basis goes to orthonormal basis. Right. So the takeaway is that I can identify the quotient complex for the spaces with quotient complex for the group cohomology with twisted coefficients. Right. So that is the first part, and then the second step is to show that the upper Laplacians have a uniform essential gap for all these quotient complexes, if and only if it has a essential gap for one particular quotient complex, which is the quotient complex of the group cohomology of gamma with coefficients in L2 of direct Hilbert sum of L2 lambda mod gamma mod lambda. So this is just so what you have to notice is that this guy, this quotient complex, this is you can look at the direct sum of all these quotient complexes L2 lambda mod gamma I, and then you can look at the Hilbert direct sum of it. This will again give you a quotient complex because you can show that the co-boundary maps are they are bounded. They are in fact uniformly bounded. So therefore, you can look at the direct sum of di. So this will give you a quotient, a co-boundary map on the direct sum, and then you can look at the closure. You can extend it to the closure. So this so I can write this as like this, and then I just apply a function analytic result that if I have a Hilbert space and if I have a bunch of bounded operators whose norms are uniformly bounded, and then I can look at a direct sum of these operators on the Hilbert direct sum of the Hilbert spaces, and if you look at the spectrum of that, the direct sum of the operators, then this is union of the spectrums of each operator and then take closure. Right. So so let's say I have a self-adjoint positive definite operator T. Then I say that T has essential gap epsilon if the spectrum is contained in 0 union, there's a gap between 0 and the next positive spectrum element. And so this implies that this operator direct sum of Ti has an essential gap if and only if all the Ti have a uniform essential gap. Now you apply this result to this because delta plus, you can show that delta plus here on the right hand side, this is direct sum of delta plus I. So that will do the job. And then finally, you have to show that you have to relate the reducedness of the cohomology, that the Hausdorffness of the cohomology with the essential gap of the upper Laplacian. So that is the last step. So hk plus 1 of gamma with coefficients in any unitary representation pi. That is Hausdorff if and only if the upper Laplacian acting on the kth quotient, the one dimension below, that has the essential gap. So how do I show that? So in general, if you have a self-adjoint positive operator, then it is invertible if and only if 0 does not belong to a spectrum. And that is if and only if the operator has a positive essential gap. So, but delta plus, but the upper Laplacian, cannot. I mean, you will always have a 0 in its spectrum because, but to avoid that, what I will do is I look at Hodge decomposition. So I look at the Hodge decomposition, which is basically just look at the image of the coboundary, look at its closure, and then look at the kernel of the Laplacian. This gives you the Hermitian harmonic forms, and the closure of the image of the adjoint of the coboundary. So let us give these things some name. So let us call it C gamma minus, direct sum C gamma 0, direct CK 0 and CK plus. And note that this guy, this is the kernel of delta plus. So what, and also D goes from here to the next one, CK plus next quotient complex. And here, this guy, this is the kernel, this is the kernel of, let's say, D. And this is the kernel of D star. And so what I can do is I can think of D just as a map from here to here. So, and I call it DK bar. And similarly, DK star, I can think of as a map from just here to here. And these two maps, DK star and DK star, DK bar and DK star bar, these are injective maps. And then I look at this. I call this the form of upper Laplacian delta plus k bar as the composition of these two, and this guy is an injective map because this is composition of two injective maps. So now I can apply this result that I had said before, the invertibility result. So, right. Okay. Right. Yes. Oh, sorry. Give me 2 minutes. I have to log out and log in. Sorry.
Did you lose him? Or?
No, he said he's going to log back in a minute.
Sorry about that. I cannot share screen. Can you?
Yeah, is there any problem, Arghya?
I cannot share. Yeah, right.
I have made you co-hosting.
Yeah, thanks. And then, sorry. Sorry. So I was saying, so I looked at the Hodge decomposition, and then I looked at these maps dk bar and dk star bar, which are kind of the maps, the co-boundary maps, and its adjoint, except that we are removing the kernels of those maps, so from the domain. So what that helps me in doing is that I can apply this invertibility result. So now we have that delta plus k bar. This has an essential gap, even only if it's invertible. But since this is surjective, injective, all it means that I have to, that is even only if it is surjective. And on the other hand, the k plus 1th homology is reduced if the co-boundary map is onto its onto the closure of its image, which is the same thing as saying that the map dk bar is surjective. And now it is kind of clear. So this guy delta plus k bar is surjective. This of course implies that dk star bar is surjective. In fact, it is invertible. Invertible, let's say. So it is adjoint. It's adjoint to dk bar is invertible, and in particular surjective. So that is one side. And on the other hand, if dk bar is surjective, then dk bar is invertible. I mean, okay, and then delta plus k bar. This is invertible and surjective. Yes. Right. So that concludes the proof. Right. So how much time do I have? Okay, I have a little bit of time. Right. So are there any questions till now? Right. If not, wait a second. Can you guys see my screen?
Yeah.
But maybe, did you see me writing?
No.
Oh, sorry, that was another window. Anyway, right. So now can you see me writing?
No, we just see this page full of examples. There
Right.
are 3 rows and 2 columns. That's all.
Right. I mean, why? Let me. Sorry. Right. Sorry. So I guess I won't go into the proof anymore. Let's see. Can you see me writing now?
Yes.
Right. So right. I won't go into the proof. Let me finish by giving some examples of such groups. So what I said is that n-Kazhdan groups will give me examples of higher spectral expanders. And but the problem is that the groups for which it is known that they are n-Kazhdan, for them it is also known that the associated simplicial complexes will be higher expanders. So these groups are, let us look at the left side of this column, left-hand side. These are semi-simple linear algebraic groups over non-Archimedean local fields. Okay, and you look at co-compact lattices, co-compact torsion field lattices in them, and these groups act on the Brouwer-Tits building, and the Brouwer-Tits building, which is associated to the group G, and these are contractible spaces, so therefore they are K gamma 1 complexes. And it was shown by Garland long ago that that the group cohomology of these lattices are 0 for all dimensions below the rank. And this was Sayre's conjecture, and he proved it for groups for which the residue field of the non-Archimedean local field is large. And to do that, what he did was he in fact proved that the upper Laplacian has a spectral gap which is independent of the gamma which you take. So in particular, it implies that if you look at xt and you look at a bunch of go modulo bunch of lattices, then these things will be higher expanders, higher spectral expanders. And his result was in fact inspired by a result on the Archimedean side. So on the Archimedean side, you can just look at semi-simple linear algebraic groups over some Archimedean local field, which means let's say R or C. And then these guys act on Riemannian symmetric spaces, which will give you K gamma 1 complex for co-compact torsion field lattices. And what Matsushima was trying to do, he was trying to look at not the vanishing of the cohomology, but he wanted to see up to what dimension the cohomology is same as the G invariant cohomology. So what that means is that you have the DRAM complex of X, and you have a bunch of forms there. So you just push it down. And these are called, whatever is pushed down, these are called G invariant forms, and they give you cohomology classes. So what he wanted to see is when, up to what dimension, that are all the cohomology classes. And for that, he used local criteria involving curvature to show that these two quantities are same up to some dimension. And Garland took inspiration from them, and he also gave a local criteria which involves links of D minus 2-dimensional simplices. If those links have spectral gap, good enough spectral gap, then there will be a global spectral gap. So that is what he showed. He found the first examples of higher spectral expanders. And what then later Ballman and Swiatkowski, they generalized this result of Garland to twisted coefficients. In fact, for all pi can be any unitary representation. Right. But that condition of residue field being large remains. And so this implies that gamma are let's say strongly R minus 1 Kazhdan groups. So this is what I meant when I said that, okay, so, or maybe I did not say it, but the same method that is used to prove existence of high-spectral expanders is the same method that you use to prove that the group itself is strongly n-Kazhdan for some n. So this does not, so the result that we showed does not give us any extra information in this scenario, but you can look at the Archimedean case, and in the Archimedean case, the result of Matsushima was generalized by Moog for any unitary representation, cohomology with twisted coefficient in any unitary representation, and he showed that the first and the second cohomology will vanish for groups with rank greater than equal to 6, and also the symmetry space should not be Hermitian symmetry. And so from our result, we can say that via the construction that I proposed, that these groups, the family of simplicial complexes that you will get from these groups are in fact two-dimensional spectral expanders. And I think these examples were not moved. So I will finish my talk there. Thank you. Thank you for listening. So,
thanks, Arghya. So let us thank Arghya for this wonderful talk. And any questions for Arghya?
So I think there's a result by So there's a result by what's his name? This characterization of property T in terms of classical property T in terms of h/1 reduced equal to 0 by Shalom, Yehuda
that's
Shalom.
true. That's true.
Right?
Right.
So, I mean, your result essentially seems to be a generalization of that for arbitrary n. Is that correct?
No. So what happens? So I think it should be seen like this: that property T, the usual definition is same as saying that the first cohomology has to be Hausdorff, and then Delorme-Guichardet plus this guy should imply that that is also equivalent to the vanishing. But in higher dimension, yeah.
In higher dimension, what?
In higher dimension, the fact that I mean the two conditions. One condition is that for all twisted coefficients, homology with twisted coefficient, you have Hausdorffness, and the other condition is that for all cohomology with twisted coefficients are 0. So these two things are not the same.
I see. Okay.
Yeah, in dimension 1, they are the same.
Thanks.
Any further question for Arghya? Well, if not, then let's thank Arghya again.